Hello, ladies and gents. You're about to get your chemistry world rocked by Mrs. Etnire and her mad knowledge.
Let's roll with Ksp day 2, yo. So these problems were common ion problems, and what that meant is we were taking an already established equilibrium and we were disrupting it by adding some sort of aqueous ion to it that would result in more precipitation being formed. So if we look at these common ion problems, there's going to be some things that are always provided to us. We will always have the Ksp of the insoluble salt in question. We will know the volume of our solution, that's important, and we'll know what the compound is that we're adding. So in this case, we want to know what our iodide ion concentration would be if we added 0.02 moles of AgNO3 to our equilibrium in question. So before we can actually do the problem, we have to process through a couple of things. One, we're adding 0.020 moles to a 1 liter saturated solution. So we need to get our molarity first. And this is going to be an easy one because we just have a 1 liter solution, but it's not always going to be 1 liter. So how do we do that? I know I'm adding 0.020 moles of AgNO3 into a 1 liter solution. So we know molarity is moles per liter. So that means I'm adding 0.0200 molar AgNO3. So now we need to figure out what ion is the common ion. So if I look at my insoluble salt, the formula is AgI. So that means my common ion is the Ag+. So the NO3 I really don't even care about. So how we know how much we're adding is based off the ion ratio and the concentration. So I know that if I'm adding 0.020 molar AgNO3, and I know that when this dissolves into solution, I get an Ag ion and an NO3 ion. What that means is my individual ion concentrations are that same amount. So I would actually be adding 0.020 molar Ag+ to my solution. So we can go ahead and we can set this up using something called an ice table. So the first thing we want to do is we want to write our dissociation equation. We want to show our AgI dissolving. Since it's an insoluble salt, we know that it's going to exist in a reversible equilibrium where it makes Ag+ ions that are aqueous and I- ions that are also aqueous. So our ice table, the I stands for initial, the C stands for change, and the E stands for equilibrium. Now, when we think about the actual Ksp expression for something like this, we know that we don't include the solid, so our Ksp is just based off of the Ag+ times the I-. So this whole area we don't care about, so we can cross it out. Now, all it tells me is that it's a saturated solution, so I don't exactly know how many of my Ag and I ions I have. I just know that it's completely saturated. So because it's a one-to-one relationship, we can just put X in as our initial concentration for both of those compounds. If we look at what we're adding to the solution, I'm adding AgNO3, and so I'm changing my Ag ion. I'm adding 0.020 molar, so I'm going to add 0.020 molar in my change situation. I'm not adding any I-, so I can just keep that at 0. And now what we're going to do is we're going to add. So I have for my Ag concentration X plus 0.020, and for my I- concentration I just have X. Now if we look at our Ksp, this number is very, 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 very small. If we look at the number that we're adding in terms of our common ion, this 0.02 molar is extremely large comparatively. So when you're doing these common ion problems, when you get to this equilibrium, you can 100% completely disregard this X number here. Because when we solve for X, it's going to be so much smaller than what we added. It's basically not going to change anything based off of sig figs. So our equilibrium concentrations are going to be 0.020 molar Ag+, and X for our I-. So we can plug them into our Ksp. So we would do 8.3 times 10 to the negative 17th is equal to 0.020 molar times X. So if I just do algebra, I'm going to do 8.3 times 10 to the negative 17th divided by a 0.02. And that tells me that this is 4.2 times 10, oops, sorry about that, times 10 to the negative 15th molar for my I minus. So if we think about these two numbers, this number is so small that when I subtract it from this number up here, with sig figs, it would just round back to 0.020, which is why we can disregard the x value here. And if you think about what's happening, it makes sense. Our KSP value always has to come back to 8.3 times 10 to the negative 17th. So if I significantly increase the amount of AG I have in solution, I've got to significantly decrease the amount of I minus I have in solution. So the only way I can do that is by making my I minus significantly smaller and forcing more precipitate to be created, which is why in a common ion problem you'll see more solid in the bottom of your test tube or beaker. I hope you find this helpful. Remember, if you have any questions, you can always shoot me an email or come in before school for help. Have a great night, guys.